Hi, I'm Radha Nagarajan from Inphi Corporation. Today we will be presenting the work we've done on an integrated silicon photonics light engine with DFB lasers and electronics. First, we'll define what we mean by the light engine. Here we have a photograph of a module that we introduced 4 years ago. It is a 100G PAM4 DWDM QSFP28 pluggable module for data center interconnect applications. The module is compatible with QSFP28 MSA form factor, has a CoW4 interface at 4 by 25 gigabits per second NRZ, and the optical output is 2 times 28 gigabaud PAM4. This is a dual wavelength module. So if we wanted to make an integrated light engine version of the front end, so if you were to look at the box, you would see the silicon photonics chip with a dual wavelength Mach-Zehnder modulators and on the receive path, germanium photodetectors. And TIA and drivers, which are external on the PC board, and 2 DFB lasers. Now, if we were to take all of this and integrate them onto a single substrate, that would be the light engine that we are presenting today. The other half of the module is a PAM4 ASIC, together with power supplies, a microcontroller, and other ASICs form the module. Now, some information on the silicon photonics chip that we had used. It's a Mach-Zehnder modulator, a depletion mode device on the silicon substrate, had a bandwidth of about 25 to 30 gigahertz. And this was sufficient for a 28 gigabaud transmission device. It's a traveling wave design. And the optical to electrical S21 data is shown on the left. The same device could be used for a PAM4 optical output or an NRZ optical output. Like most Mach-Zehnder modulators in silicon photonics are, it's a direct coupled device driven by a differential pair architecture in the driver. On the receive side, we had integrated germanium photodetector on the same substrate. The S21, small signal S21 of this device shows that the bandwidth is in excess of about 18 gigahertz. We did not need a lot of bandwidth for this particular application, and we had limited the bandwidth to mitigate input noise into the receiver. And the dark current at fairly high temperatures, in this plot only shown up to 50, is in the range of about 1 to 5 microamps. Now for the light engine details. It is 2.5D integration of the optics, which is based on silicon photonics, and the electronics. The silicon photonics chip is used as a carrier or the interposer for the transimpedance amplifier on the receiver side and the driver on the transmitter side and the laser diode as the optical source. The TIA, the modulator driver, and the laser diode are all flip chip bonded on a silicon photonics die. The high-speed signals are wire bonded, and this chip has an integrated on-fiber coupling. First, the TIA and driver assembly. The TIA and driver are first plated using copper nickel tin gold bumps. And after reflow, you get this classic shape of the copper pillars. They were on a 100 micron pitch. And the silicon photonics had an UBM layer, copper nickel gold plated pads. The copper pillar would bond on to the pads on the silicon photonics. The bottom right-hand corner shows the TIA and driver patterns for the copper bumps. They were then integrated onto the silicon photonics chip shown on the top right-hand corner. And to the left, you see the TIA chip, and to the bottom right, you see the driver. And the laser chips are over here, and the fiber interface is in blue as shown. These devices that show up in gold are actually single layer caps, which were used on the light engine for decoupling the driver, power supplies, and the TIA power supplies. First, the flip chip TIA and driver performance were independently measured. There is a test port on the silicon photonics substrate that allowed us to test the TIA and driver independently using probes. This is the probe setup that's shown here on the top left-hand corner. The on silicon photonics driver response is a 3 dB bandwidth in excess of 20-25 gigahertz. And the on silicon photonics differential TIA response at a bandwidth, actually quite a bit in excess of 20 gigahertz as well. And the performance on the on-chip die were equivalent or essentially the same as the on-die performance before integration. Next comes the laser diode. We had picked the CWDM laser diode, although the original product was a DWDM product. For the demonstration here, we picked a 1270 nanometer laser diode. What we've shown here is not the chip, but a test coupon where the lasers were integrated and wire bonded. You can see 2 of these slots filled as part of the development exercise. And when integrated, this is the laser diode integrated onto the silicon photonics die. And we measured the performance of this die. On this test coupon, there was a vertical coupler right where I'm pointing. So we could measure the output power directly coupled to a fiber. This is the LI curve supplied by the manufacturer, LIV curve. And this is the measured LIV curve. We have about a 3.5 dB loss, which includes a vertical coupler, laser coupling, as well as the detector that was used to detect the light at the other end. So the coupling loss is of the order of 2.5 to 3 dB into the waveguide on silicon photonics. So one of the things that people are worried about is back reflection in our method of integration. This is the optical spectrum, a very high resolution optical spectrum. This is just a 10 nanometer span of bias between 16 to 80 milliamps in 2 milliamp steps at 30 degrees C. You can actually see the LI curve on a log scale as the power goes up. When you bias from 16 to 20 milliamps, this wavelength shift is thermal, but there's no back reflection. The spectrum is clean, free from characteristic reflection signatures at all bias points at just above threshold. The SMSR is better than 40 dB from just above threshold all the way up to the operating. We had also run thermal and stress model of the laser. The primary goal was to figure out what the thermal resistance of the laser was. The lasers are actually sitting here. These are the thermal simulations. As you can well tell, the hot spots are essentially where the driver, the 2-channel drivers are and where the lasers are. And rest of it essentially at the substrate temperature of about 70 degrees. And you can see some hot spots on the TIA. As for the stress, similar pattern here. The highest stress points were around the driver area. We measured the thermal resistance. The way thermal resistance is measured for laser diodes is first you measure the wavelength shift with temperature, and then you independently measure the wavelength shift with power. One divided by the other gives you dt dP, which is the thermal resistance. This is a 300 micron DFB device and had thermal resistance of about 60 degrees per watt, pretty much in line with what we had expected. Next comes the testing. The die is actually very small. You can tell this in relationship to the size of the probe needle that we had used to bias the laser. In this particular case, the trace for the laser had not been bonded out. And this is the RF connector bringing in the transmit signals. And this, the RF connector for the RF signals is just beyond this photograph, but these are RF traces running on the board for the RF traces running on the board for the TIA output. This particular chip was biased using a series of bias boards and had an external data coming from one of our chips developed at Infon. This is the PAM4 optical output from an integrated light engine. There are a number of reasons why the eye opening is not as good as we had anticipated. A large part of the problem was the PAM test board that we had used to drive the light engine had a very long RF cable. So the PAM4 optical output suffered from quite a bit of the RF impairments in this breakout cable. The overall performance, as I had just mentioned, is impacted by the RF, and a fully integrated version where this driver chip is integrated right next to the light engine would not suffer the same penalty, actually does not suffer the same penalty. We have since gone on to make another integrated version of which we'll share the results at a later time. One of the other improvements we had also made was to take the data rate at 100 gigabit per second, or 53 gigabaud PAM4, for which we have developed Mach Zehnder modulators with a much larger bandwidth, and germanium photodetectors also with a much larger bandwidth. With this, I come to a conclusion of my talk, and we'll take any questions going forward. Thank you.
Hi, I don't know if you guys can all hear me. I'm online, and if you have live questions, you can ask or type them into the box.